Hi everyone, welcome to my talk, Forget About AI and Do Mathematical Modeling Instead. Before I start, a few words about myself. So I'm a mathematician by profession. I've worked for about 10 years in the field of data science, typically bringing stuff into production, mostly on the Python data stack. So just a little bit about me. So where do I work? I work for Innovex, and we are an IT project house with a focus on digital transformation. So we basically offer everything from back-end, front-end development, operations, also trainings and so on. And also, of course, we have a huge data department where I work, where we have a lot of data scientists, data engineers, ML engineers. But coming to my talk, and you might actually ask yourself, why this title, right? Why should I forget about AI? Might be even provoking for some. And the thing is that if you look at all the news in the lately, and it all seems like it's like the wonderful world of AI, right? You see that AI is outperforming humans in designing floor plans, for instance, for microchips. You see that even our physicists are outperformed. It seems like AI is doing everything much better than humans, and there's like one success story after the other. Also, really complicated things like summing up a research paper in a few sentences. I mean, for humans, this needs a lot of practice and a lot of domain knowledge, and it seems like, okay, AI just does it. So this is what you see if you read like popular news articles on various websites or in magazines. But is this actually true? So, for instance, you remember there was COVID, right? And there are a lot of people in the beginning tried, so okay, let's use data science and all the data to actually solve COVID and help our physicists to, our physicians to actually detect COVID and so on. And there was one paper that looked at all those approaches to actually help with COVID, also with predicting things and so on. And it seems like all over those 2,000 projects, they did not really add any value in defeating COVID. And then there's also things like in the field of recommender systems. So this is one of the fields that I also work in. It seems like most people, they don't really want to use old robust methods anymore. They rather spend millions using some fancy AI and get actually worse results than some really simple method like a matrix factorizations. Then one thing that I found really interesting was that there was one AI paper that showed that AI can even do symbolic things, like you give it an equation and ask it to reorder it and so on, and verify if an equation is right or wrong. And then a few months later, there was another paper saying, okay, what you did was actually completely wrong because your test set was extremely biased and really simple. So like the main takeaway was like in this Twitter message, like shown here, that if you are a scientist and applying your cool machine learning AI method, then you should at least take this domain a little bit serious. So even Andrew Ng, I mean, he's really famous. He once said that that most of the times, like the AI works on test sets, but from this test set, it's a long way to actually apply AI in the real world. So it's not so shiny and sunny as you might think in the real world. So don't get confused by reading all those nice success stories. So one of you surely knows this Gartner hype cycle. So my take on this is that we are really just behind this peak of inflated expectation, because everyone seems to talk about AI right now. And if you have any kind of business problem that has a little bit of data, people think to, yeah, okay, just apply AI and it will solve it, right? So this is actually the reason for this talk, that I want to give you a different angle on this. So, and what is meant by AI actually? So AI, surely you can read a lot of papers and old books what AI means, a symbolic AI, rule-based system. But nowadays, if people talk about AI, what they actually mean is machine learning and especially deep learning. And we've also in the morning, there were some talks about neural networks, deep neural networks. And basically, this is meant by AI most of the times. And what's interesting now is that the expectation is that, yeah, you just give it some data and it will magically do anything, right? So this is the kind of message you have from a lot of, from all those success stories, and people start to actually really believe this. And I think this is definitely not true to that extent. So I myself also had, of course, some experiences in my work life, and I want to share a few anecdotes. So there was once a colleague, and he was on a project where he had to predict the efficiency of nuclear power plants. So he had a lot of data. So his background was some economical background, a really good data scientist. And so he applied a lot of machine learning methods and could actually predict the efficiency of nuclear power plants quite well based on some sensor data and so on. And when he actually presented his results to us, he said like, well, and there's this one feature who's like really, really predictive of the efficiency of the nuclear power plant, and it's the outside temperature. And so for him, it was like, wow, the outside temperature really is it's important for predicting the efficiency. And then one of the physicists in the room stood up and said, well, this is the second law of thermodynamics. And you could have actually seen that there's the Carnot efficiency, and if it's defined like that, so you basically have the temperature of the cold, so the outside, and the temperature within the power plant, and you have like a limit of what the efficiency can be. So I'm no physicist. I hope I made this correct. But for me, the impression and what the takeaway was in this situation, that domain knowledge is so important if you want to solve a problem. Another thing, another project was about like finding the right packaging, right? If you order something online, you take a lot of goods, and if you buy it at some store, in the end, someone has to pick those goods and put it in packages with varying sizes. And there's not only 3, there's like 10, 20 different package sizes they can pick from. And the question is, since you can have and pick different kind of goods, what's like the perfect package size? Not too big, not too small. And when we talked first about this problem and how to solve it, the first idea was, okay, we have years of data already for this, so of people having actually picked a package for certain kinds of combination of goods. So why not just apply some deep learning approach or whatever and find this mapping? And well, you can do it like this, but then, of course, you have to think twice, because it also gets you in a lot of trouble. First of all, you have a bias in the data, because if you are someone packaging those goods, then it's better for you to pick it a little bit, to take a little bit larger package size, right? Instead of taking a smaller one and in the end having to move the stuff out again because it was too small. So there's this. And the other thing is, what happens if one day people decide to use other package sizing? So you can actually solve this problem much easier by looking up. I mean, if you studied computer science, you have surely heard about the bin packing problem, and it becomes way less fascinating, way less sexy. It's no AI anymore, right? But still, it's a robust way to solve this problem. And since people are not going to pick 100 goods at the same time, they're heuristics to solve this problem really efficiently. Another thing is that some of real-world problems like COVID, you're not really only interested in a prediction, you're also interested in an inference. For instance, this paper showed that, or tried to show that what the actual impact of different political measures like closing down schools or that you have to put on a mask, if those measures actually change the dynamics of the COVID pandemic. And this is something you could not have really done with AI because you rather have the information of how pandemics behave and try to infer like this change point that you don't know about. I mean, you suspect it's the point in time when certain political measures were applied, but to actually prove this, you have to make an inference about something that you don't know. And this is these are fields where AI doesn't really help you, but more mathematical approaches help you. So this were just like some anecdotes. And to make this a little bit more systematic, I want to give you a short overview of the downsides of AI and especially deep learning that you have to keep in mind if you want to apply it. So first of all, in many, many business cases, you have a need for interpretable models, right? Whenever you have some high-stake decision-making, then, for instance, in medicine, in law enforcement, banking, in many, many cases, you actually want to tell someone why you made this decision. And this is problematic, of course, with neural networks because it's a black box, basically. You also have to be transparent about certain assumptions and biases. I mean, there's a lot of debate about diversity and that you don't discriminate against minorities. And how can you prove that whatever you are doing is not discriminating if you don't really understand it? And their simpler models can be much more interpretable than AI or deep learning. And of course, then there's also the trust of users. So if you don't really understand it, then it's really hard to build trust. And actually, so this is not something that it's completely new. So people thought about this, and they came up with this field of explainable AI. And I think this is a wrong way to go into, because explainable AI is basically give us ways to understand what the black box model is doing. And there's this excellent paper of Cynthia Rudin, and I took this example out of this paper, that explaining a black box model is nice, but really not enough. First of all, in this case, it's wrong. So you have this Siberian Husky, and it detects, like, this is a so-called saliency map showing that this is the part that lets the neural network decide that this is a Siberian Husky. By changing the photo a little bit, like with some adversarial attack, you can also convince the network that this is the part that it's a transverse flute, which is, of course, not. And the main takeaway is that you don't really want to explain your model. You want to explain your world. So if this was an interpretable model, it would tell you that because this dog has a long nose and maybe a white face and pointy ears, it's a Siberian Husky. This would be interpretable because you kind of relate it to something you can understand. People just don't think in pixels. So explainability is not what you need interpretability. Then another thing is, do we actually have big data? So deep learning methods most of the time need a lot of data. I mean, of course, there's few short learning and zero short learning and all those things that allow you to do this if the domain is really close. Of your problem to a domain where you have a lot of data. But so from my perspective and from my experience in many, many business problems, you don't have that much data at all. For instance, I worked a lot in retail and predicting the demand of the next week to make optimal replenishment. And if you have something like this, like if you want to predict the number of sales over Christmas. Christmas is like completely different every year, depending on how the vacation days changes. And if you even have like 5 years of data of a shop selling things, then looking only at Christmas, the time over Christmas, it's really different every year. Because the days change when Christmas is. So if it's on a Monday or Tuesday or Saturday or Sunday. And so in practice, you don't have big data so often. Then there's interpolation versus extrapolation problem. So I don't want to go too much into this detail. The problem is that if you are like moving far away from your training data with neural networks, then you never really know what your result is going to be. And this is also difficult for humans. But the problem most of the time is that you don't know with neural networks. If you moved away from your training data, you're just going to get a result. So to sum this up, so we have, first of all, the problems with the data efficiency. So AI is quite data inefficient. It's definitely hard to explain and to interpret. It lacks robustness and also trustworthiness. And a neural network always reflects the biases from your data. I mean, you've maybe heard also the story where webcam, which should follow your face, did work only with people with a white skin color, because it was not really the data was extremely biased towards like European skins, and this is something unwanted, right? So it's discriminating, and yeah, you will always have it reflected in your neural network, except you put a lot of care into like curating your data the right way. And the fifth and maybe most important part is that it's really hard to reason about a neural network and to gain further insights. So let's say even if your neural network works perfectly for the use case, you kind of get an answer, but do you really can gain more knowledge about your actual use case, about your business problem? So just think maybe when you hear the word AI as a database with a fuzzy index. So this is always the explanation I use for non-technical people, because in the end, you have a lot of training data. Somehow the training data is in a way still in the weights of the neural network. And if you ask the neural network for something, you're going to get kind of a strange mixture of all your training data out of it. You can see this, I think, in a nice way also with the DALL-E 2, so this image generator, or a robust diffusion, where you give text and some images are generated. And of course, all those images, they have a certain similarity also to the training data. I think of it like just some multi-dimensional distribution, but it's a way, in a way, it's a database with a fuzzy index. And now we've seen a lot of like downsides of AI. So with a little data challenge, I want to show you how actual people right now are thinking when they see a new problem, and what I think should be changed about this. So let's say I have a use case. I just grabbed some data from the website or some kind of Kaggle challenge, and I have a feature and a target, and I want to apply some machine learning on it. So I split it into train and test data. So the black the black points are now my test data, and the white are my train data. And let's say I apply from scikit-learn a lot of different regressors, so linear regression, random forest, MLP regressors, so some neural network, and you see that it's fitting really well. You could be like, well, it looks really good. But what happens now if I ask for something that is way beyond. So this is now extrapolation. You see that the linear regression does how it's named. So it kind of extends the line linearly. You see that the random forest like keeps the same height as the last bin, the last leaf in the tree. And the neural network, yeah, depending on what the initialization is, will do all kinds of stuff, so you never know, actually. So this is the extrapolation problem, which is extremely hard in like low dimension, higher dimension. It's actually hard to decide if it's extrapolation or interpolation. But the actual point is now that so far we haven't really talked about what the feature is, right? So this is the main takeaway, because if I tell you now that the feature we have is actually height, and this is the time, then this is a slide that took me the longest, by the way, to get this right. Then you could say that this is just a free-fall equation. This data was actually captured by students letting a ball fall from different heights. And so if you know the use case, and if you think about the use case, you can just look up in your physics book that you have the free-fall equation, and then the green line actually give you the result. Of course, that's a really simple, it's a really simple case, but it actually came up when at Innovex we have this InnoCube. And so innovation circles, we call it. So we have a certain time and budget for people to try out innovative things. And so we have this, let me see if this works. So some group actually built this InnoCube. And this is more or less some IoT device, which in real time like sends the data to this web interface, which is, it's working. So you see that when I move it, it's like in real time rendering the position, and we also have the temperature in the room, so it's 24 degrees. And one said, okay, we could implement another feature like what if you want to have a throwing challenge, how far you were able to throw the cube. And so how did we solve it? So the first idea actually was, so let's apply AI. And then one of the mathematicians in the room, like it was not me, said like, well, maybe there's a simpler way to solve this problem. How high this cube is, and it's not working. So much about live demos. But what you should see is that it should track it, and the actual point is, so just imagine you see some bars with the height here. The actual point is, and I'm gonna switch back to the slides, the actual point is that even my Mac is not working anymore. The actual point is, so here it was eight throws, you saw it. And you believe me that also this you can just solve with a free-fall equation, because you know what goes up needs to come down, and just like using a sensor to find the points between when it leaves your hand and when it gets back, you can apply something much simpler than AI to get the height of this. So now, what is mathematical modeling? When I've talked so far about a model, basically what you can think of it is like we have data, we have an algorithm, and we train it, and in the end we have a model, right? So this is also the case for AI and also for for mathematical modeling. So where's the difference? And the difference is within the algorithm, because in the AI ML world, so this is what most people now tend to, you take an algorithm like a neural network, something that is tailored to approximate any kind of data. So this is this universal approximation capabilities that a neural network has. So you choose an algorithm that can adapt to like anything. And now in the mathematical world, you actually want to have this algorithm like really describing the actual problem. Like if it's a physical problem, this would be some formula. But in many cases, like if you describe a marketing problem, you can also describe certain relations and really boil your model down to simple formulas with maybe a few unknowns where you can use then the data for to fit it. And this is the two perspectives. And like a more like formal explanation is, I found this by Arnold Neumeier quite nice, is that basically mathematical modeling is the translation of a problem from the application area, so business problem, into the world of mathematics, solve it there, find some nice results, some analytical analysis, and then like use those results to get more insights about your actual problem in the real world. And I mean, this is in the end what we are after, right? So we are given like real world problems and we want to solve them. And if it's in the end some AI or mathematical model is maybe not of interest, but you should always be interested in really like solving the problem and not just say whatever comes, I will apply AI to it. And you've surely seen this Venn diagram 1,000 times. I mean, this is also what's a huge part of data science is that you have to be a domain expert in the field where you want to try to solve problems. So understanding the problem and domain knowledge is key. And simple things, so simple trumps complex most of the time. And a neural network is something really, really complex. So if you can solve the problem in an easier way, it's going to be more robust and more interpretable, and you're going to get maybe also more insights while doing so. Of course, it's no black and white, it's a spectrum. So even on the left side, where I put deep learning and like convolutional neural networks, even they have some assumptions, some modeling in them, because those kernels that go over the image, maybe you've seen the talk in the morning. This is actually in the neural networks because you want to have a position invariance, right? So if I stand here, I'm a human. If I stand a few steps further to the left, then I'm also a human. And this design in convolutional neural networks that you have those kernels going from left to right, from up to down, from top to bottom, this is actually a kind of modeling of the fact that you want to have or detect positionally invariant. And but all the rest is actually, the data is actually used. So in the middle ground, so typical machine learning things like this is a decision tree. There you have a mixture because a lot of your time will go into feature engineering, and feature engineering allows you to actually use your domain knowledge to come up with a new feature and also add maybe certain certain constraints you have, and basically your domain knowledge inside the feature and design smart feature from your understanding of the business problem. And then the right side, where it's then completely mathematical, like in this Cauchy equation here, Cauchy momentum equation, and so in the end, it's a spectrum, but so my point is that you should try to be as mathematical as possible and only rely on deep learning if there's really a need. And just to tell you, so what then the mathematical model cycle typically is. So most of the time you start with some real application, with some real problem, like in this case, how much sand is in the container. So a real container, no Docker or anything, so how much sand is in there. And of course, the people asking this question is not interested in how many grains of salt are in this container. So the first step is to like abstract away and say, okay, actually you are interested in the volume of the sand, and somehow I have to calculate this. So this would be the real model. And then moving over to the mathematical model where you do further simplification, tell, okay, maybe the container looks like a prison, and I know how to calculate the volume of this, and I can solve this, and I get the results and can check back if this is makes any sense, and maybe think, okay, maybe there's a pile of sand on it, so I'm not close enough, and so on, and go through the cycle several times until my mathematical model fits and solves my actual problem. But this is a much further, much nicer way of approaching a problem instead of just saying, okay, give me some kind of data and a deep neural network, and I'm going to apply it, which in this case would also not really be possible. So to sum this up, when should you actually apply more mathematical ways? So when to do mathematical modeling? First of all, if you want to gain insights into your data, if you want to integrate your domain knowledge, if you have structured data like tabular data, if you have sparse data, if you have not enough data, then that's typically really well for mathematical modeling. If you have feedback loops, so if your problem is changing while you're applying it, think of a recommender. So if you have a recommendation model in what items you're interested, then this will also change your future data, so you get some feedback loops. And if you have high-stake decision-making problems, if you need the interpretability, and if you also want to predict a certain uncertainty, then mathematical modeling is really well. But when it's not so well is, of course, for unstructured data. So if you really want to predict if this image is a cat or a dog, then, of course, this is the field where deep learning really excels. Also, when you don't have any domain knowledge available, or if you really need like short-term results, because like mathematical modeling most of the time takes some time, and it's not like you just call an API with the data and get some results back. And with this, I want to come to the main takeaway. So for me, mathematical modeling is really about understanding the problem. And I hope whenever you get to solve another business problem, so that your first thought is not, okay, how can I apply some deep learning model here to solve this business problem, but rather, okay, let me further understand the business problem, let me formalize it, let me write it down, and then solve it with a method that actually fits the problem. And this will definitely not always be deep learning. So with this, I want to conclude. Thanks a lot for your attention and time, and I'm happy to answer your questions. Thank you.